Okay, so again, like, so half-life, again, half-life time period required for 1/2 of the reactant to disappear. In a first order reaction, the amount of time for 1/2 to disappear is the same. Oh, what happened? Can't, oh, thanks, guys. Wow, it took me forever to see this. Can you see my screen now? Wait, here we go. It presented and then it stopped presenting, I guess. Now you can see it. I can't hear you either. Can you see my screen now? Okay, you can see it now. I couldn't hear you if you were trying to speak to me. Sorry about that, guys. Yep, smile and wave, boys. Smile and wave. Yep, I didn't hear you. I didn't hear you. Sorry about that. I just talked to myself for a while. All right, let's do it again then. Good thing I'm gonna do it again anyway. Okay, so here, determining half-life. So y'all can see this, right? You guys see my screen, you saw this presentation, you can hear me. Okay. Usually I have my other computer that I can put you guys on the other screen and I can see what you're saying, but I don't have my other screen. I'm at school today and I don't have my good setup. I'm here to take the video for our invitational today. The Science Olympiad Invitational. Okay, anyway, so we're good to go. Okay, back to this. So half-life, half the amount of time 1/2 the reactants disappear. In a first order reaction, it's consistent. It takes the same amount of time for the first half, and the second half, the third half, fourth half, fifth half. Always takes the same amount of time. Okay, that's a first order reaction. Okay, and if you're graphing concentration versus time, right, in a first order reaction, you're not going to get a straight line, as we know from the integrated rate law, right? You're going to get this. Basically, it's really a decay, right? It's a logarithmic decay, or natural logarithmic decay, really, right? Logarithmic decay over time, right? If you were to graph the natural log of concentration versus time, you get a straight line because it's consistent, and the change in concentration is consistent, or really the half-life is consistent. So here we go. The data points plotted on the graph picture left represent concentration time data collected for radioactive decay of element Q. While you may at glance be unable to determine the order of this reaction, you can definitely determine which order it is not. So which order do you think it is not? Well, if you look at it, it's not a straight line. It's concentration versus time. If it was a straight line in concentration versus time, that would mean it was zero order. So it's not zero order. It's definitely not zero order. Okay. Next thing, what is the half-life of element Q? Well, element Q, half of it, it starts at 1. In order to get to 0.5 or half of it, you need 3 minutes. So the half-life would be 3 minutes. Okay, 3 minutes. What's the molar concentration of element Q after a second half-life? So you have 0.5, and then half of that would be 0.25. So 0.25. Okay. And then at that point, 75% of the original would have decayed already. So because that's 75% decayed, there's only 0.25 left. So that would be at 6 minutes. So it is not zero order. Half-life is 3 minutes. And then 0.25 and 6. Okay, really, really simple. Okay, again, what I was talking about here, and you didn't see it before, but I was talking about this: zero order, first order, and second order. In a zero order reaction, the concentration versus time data is a straight line, right? And the half-lives get shorter and shorter and shorter as we go. Basically, it's the amount of the change in concentration over time is consistent. It's always the same. So the amount of half of it to disappear and turn to products is going to get less and less, because you're going to have less and less reactants as you go. You have less and less reactants as you go. The time it takes to change reactants to products gets less and less. Okay. First order reaction, the half-life stay consistent. They're equal. They're always the same. And most of the calculations we do will deal with first order reactions. Okay. And then finally, second order reactions. Second order reactions, they happen really fast at first, and then they start to slow down. So the half-life is really short in the beginning, and then it's much longer in the end. So it takes much longer for half of the stuff to disappear. Okay. So again, most of the time we'll only be dealing with first order, but we can do 0 and second order. Okay, first order, if we want to just use an equation to figure it out, these are the equations we're given. T1/2 equals the initial concentration over 2K. That's for the 0 order reaction. Okay. And K is the rate constant. For first order, it's really simple. T1/2 equals 0.693 over K. And for second order, it's T1/2 equals 1 over K times the initial concentration. Again, this one in red, that is given to you specifically, like that exact equation is given to you on your cheat sheet. These other two are not. However, you can derive them from this, from the integrated rate laws. You just say like, this is A naught and this is A naught over 2. So A naught over 2 would be the half of the original concentration. Same thing here. You'd have 1 over A naught on this side, and you have 1 over A naught over 2, or really 2 over A naught, right? Because you can do the reciprocal of it, get that. Okay, I do one of those in the homework. I think for tomorrow. I think the work tomorrow. I derive this, take this one, and derive this one. You could do it if you want. It's just 2 over A naught equals KT plus 1 over A naught. And you'll see that it comes out. You do 2 over A naught minus 1 over A naught, you get 1 over A naught. And then divide by K, you get 1 over K A naught. That's what you get here. Super, super simple. You do it for this one too. Comes out the same thing. Okay. This chart is really, really good to kind of know. I wouldn't really necessarily memorize it, but it does help a little bit. It does help. You kind of look at these and know all of this. Really does help. And then that activation energy I talked about in the beginning, where you don't have to do the Arrhenius equation. Okay, you don't have to do any calculations. Just know that the Arrhenius equation relates to temperature and rate of an elementary reaction. So the activation energy. Okay, but you don't do this equation on the test anymore. Okay. Okay, so the work you have to do is here, kinetics half-life. The answers are provided, but do try it on your own first before you just look at the answers. It can be a little confusing at times, but try the best you can. Hopefully you're good at your algebra and with natural logs and all that stuff. There's a little bit of that in here. Okay. And then tomorrow we're not meeting for class. But this work here will be due tomorrow. And then Thursday we will have class, and I'll answer any questions you might have on any of the work from today or tomorrow. And then, yeah, I'll make the assignment for Friday as well very soon. The test will be shortly. And I don't think I'm going to make you do the bookwork for this one. So if you started doing the bookwork, you don't need to. think we're not going to do it. Save yourself the headache, okay? You were doing it? That's okay. It helps. Okay, well, that's all I have to say. Does anyone have any questions or comments, concerns related to AP chemistry, related to life in general?